Hello there, ATS EVS 105 students. Dr. Schrage here, and I'm going to give you a lecture now that comes from parts of Chapter 2 in your textbook, and it's going to be a combined lecture that's going to talk about changes that we have observed in the ocean and changes that we have observed with regard to ice. The fancy schmancy word that we're going to use for all the ice on Earth is going to be the cryosphere. This is a combined two topics here, in part because I wanted you to get used to the idea that you can navigate through these lectures using the tools that are on the sidebar off to the left side on the website where you're reading this stuff. You don't have to make it through this whole lecture in one sitting. There's a reason why I don't record like a 1 hour long YouTube video. That would be a hard thing to work with, especially if you had to stop in the middle of it. This way there's tools along the side that can say, hey, I got as far as question 2, and you can then move on to question 3 when you come back, or whatever. Or you got through the first part of the lecture, now you want to move on to part 2. So anyway, I thought it would be useful to kind of, for lack of a better word, help train you to know about those tools on the side there by kind of combining these two topics of the oceans and the cryosphere into one block of material in this, into one lecture like this. This does come from pages 20 to 25 in your textbook, as well as I think I had you read the executive summary about the ocean from the IPCC 5th Assessment Report. So those would be the two documents that I hope you have read and or will read after watching this lecture. Let's start by talking about the oceans, which cover, of course, something like 70% of the Earth's surface, and we would want to know how they are being what kind of observing systems do we have to monitor what's going on in the ocean? What kind of changes have we observed in the ocean, and so on? It's probably not going to be hugely surprising to you to find out that much of the heat that we have observed being trapped at the surface of the Earth by greenhouse gases, again, we'll get in a later module as to how that's all done, a lot of that heat ends up in the oceans themselves. Now, just to be clear here, your book sorted this out perhaps differently than I would have. They're saying this is for the bulk of the ocean, not just the top of the ocean, the surface of the ocean. Their discussion about the surface of the ocean, the author folded that into talking about the surface. Our last lecture was called about like temperature changes at the surface of the Earth, and that included over the ocean, okay? We're not talking about that now. We're talking away from the surface, down deep in the ocean. Changes there are going to be kind of amazing. I mean, it's kind of astonishing to think that there could be changes to the temperature, for example, of the ocean, you know, hundreds of meters from the surface where the heating is actually happening. But we're going to see that there are changes up there. And I'm just going to give you a figure here that I found on a website, and I have provided you the link there. It's quite similar actually to figure 2.7 in your textbook, though, that it shows the temperature trend on the surface of the ocean. Now, the copy that you have in your textbook uses units of degrees Celsius, and I believe the observed global change average over the ocean, I believe it's average over the first 700 meters of the ocean, from the surface down to 700 meters, was about something like 1/10 of a degree Celsius. I don't remember the exact period of time over that diagram, but I just remember those were the units. In contrast, the diagram I have here is actually talking about the total heat content of the ocean, measured in 10 to the 22nd power joules. Okay, that's not maybe a unit that you're familiar with, but they're both measures of heat, okay? Joules are measures of heat, and Celsius is degrees of temperature. But you can definitely see that extending back, you know, like in this case to the 1950s, we can see that there's quite a dramatic temperature change in the ocean. Again, we're away from the surface. We're talking like the top 700 meters or something of the ocean here. And my goodness, the amount of heat added has been quite dramatic. And you might wonder how we know that. I mean, how would we know that the temperature is changing in the ocean, or the amount of heat being stored in the ocean is changed? Well, you might remember that in the previous lecture we saw that there's quite a network of buoys out in the ocean that are measuring properties of the ocean and the atmosphere near the surface, like sea surface temperature and so on. But many of those buoys are chained to the bottom of the ocean. The right word for a buoy that is chained in that way is that it is a moored buoy. Moored buoy is a hard word to say. A moored buoy is moored to the surface to the bottom of the ocean. You can see in the schematic diagram here, it actually kind of looks like it. The way they attach them to the bottom of the ocean is usually using old railway axles, like from railway cars that aren't used anymore. They weigh a ton, and there's tons of them on the open market. So you know, entities like the National Oceanographic and Atmospheric Administration buy these old, heavy railway axles, and they use them to anchor the moored buoy in place, and then at various places along the length of that chain, they install instruments to measure the temperatures at different locations. So there's different sensors along that length of chain. There are other cool technologies that we could use to measure the ocean too. I can't remember the name for this instrument that they toss it off the back of a ship, and then it's deployed for months at a shot. It has mechanics on board that change the level at which it'll float in the ocean. So it'll it'll descend down to about 1,000 meters, and then it'll dip down farther, and then it'll buoy itself back up to with compressed air up to the surface and radio its results back to a satellite and so on. I want to say these are called CCDs, but I can't remember the exact name right now. But there's lots of these kinds of cool technologies out there monitoring the ocean. And all of them are a maintenance nightmare, and we spend a lot of money maintaining them. This guy hanging out on the buoy here that you see here, this is actually my college roommate, who is an environmental scientist, and he works on a ship that is funded by the National Oceanographic and Atmospheric Administration, and they go around maintaining these buoys. The buoys are wrecked by storms, and they get hit by cargo ships, and they get salt built up on them, and birds poop on them when they rest on them, and so on. And he sent me this goofy picture one time of him just sitting on a buoy, and I thought I'd share it with you. Anyway, we really spend money and resources maintaining these pieces of equipment, okay? They go out there, they service it, they have ways they can, you know, pull up the instruments that are along the chain and so on, and they can make sure they're all calibrated and working and all that kind of good stuff. We spend time and energy making sure that all of these observations are taken to a certain quality. And, you know, for example, from that, the IPCC report can provide us with, you know, pieces of information like what is the temperature trend. And while the overall trend for the oceans is warming, and a relatively small number, like 0.1 degree over the last 50 years, or whatever the units are in the book, you can see that there's actually places on Earth where there's a great deal more warming. It's very regional. For example, the deep ocean has been warming a great deal over the North Atlantic and parts of the North Pacific. Okay? That's a big amount of change. I mean, that is a warming of 0.3 degrees Celsius per decade. Okay? Over a course of a century, that would be 3 degrees Celsius of warming. That is a lot of warming. I mean, you know, these temperature changes are not huge, but they have a huge impact on the creatures that live in the ocean. I mean, there are very specific ranges of temperature under which eggs mature, or shells form, or whatever their food lives. And they also there's climate implications. I mean, this is an enormous amount of heat. I mean, this is a big, thick layer of the ocean we're talking about. You know, these statistics that we've been seeing so far have been for like the 0 to 700 meters of depth layer. That's a pretty thick layer of the ocean. And it is a big part of what is responsible for sea level change. Oh, now, sea level change, that's something that the public has sort of latched on to, this idea that the oceans are rising. And we'll see that that's true, but it's a little bit complicated. In general, the subject of the height of the sea level is a topic that's very complicated. It's more than just the temperature of the oceans. It's more than just melting of ice. The continents themselves move up and down for complex reasons involving things on geologic scales and so on. And so it can be very complicated to sort out the business of sea level change. But from the point of view of climate, you know, if you're talking about just climate processes that can change sea level on the scale of like a human lifetime or whatever, there are really two main ways that climate can result in sea level change. One of them is the one you're thinking of already. That's the melting of grounded ice. Now, by grounded ice, we mean ice that is above sea level, things like glaciers and ice caps and things like that we'll talk about in the second half of the lecture. This is part of the water cycle that is now trapped above sea level, and when it melts, it drains down through, you know, rivers and streams and so on, back down to the ocean, filling the ocean further. That is part of the story. In fact, that is a big part. In fact, that's more than half of the story of why sea level is increasing. But another important part of the story is thermal expansion of seawater. When you heat water, water expands. Just like most materials expand. They have a thermal coefficient of expansion, to use the correct term or whatever. But they have a just like most materials that expand when they get warmer, we have to take into account the fact that ocean water expands. Now, we don't normally think about this in our day-to-day lives. I mean, if I put a cup of tea into the microwave, I don't have to worry about, well, it was pretty full, it's probably going to expand and overfill the cup, as you're going to see. That's a problem. But the oceans are huge, and even a little bit of expansion of each, let's just say, gallon of water, if it expands a little bit, well, there's a lot of gallons of water in the ocean. It's going to result in a great deal of expansion, and there's no place for the water to go but up. The oceans can't expand downward, they can only expand upward. Let me show you an example of why this is something you don't notice in your day-to-day life, but has a huge effect in the ocean. Here's a cup of water. Just for numbers I was plugging into a spreadsheet trying this out, let's say there was 7 centimeters of water in this cup, okay? It's a fairly small cup, okay? Anyway, I plugged it into some calculator, a spreadsheet that had calculations in there about and then you change the temperature this much, how much will it expand? So I warmed the cup of tea up 50 degrees Celsius, got it most of the way to boiling, because it probably started off at room temperature of about 20 degrees Celsius. And if I did that, it turns out the water will expand by about 1%. So it'll expand about, if it was 7 centimeters before, it can't expand horizontally, it can't make the cups push out on the sides, it's got to go up, and it'll raise the level of the water by about 0.07 centimeters. Okay, that's less than a millimeter. There's no way you're going to have noticed, oh my, the cup looks more full now that I've warmed it up. No, you would never notice that. And that was a big temperature change, 50 degrees Celsius, but there wasn't that much water there. Let me show you an example here for the ocean. Consider the top 700 meters of the ocean. If I warm that 700 meters just 1/10 of a degree Celsius, which is pretty realistic, a percent at which it will expand is not all that much. It's, what is this number? 0.00207 is what I got from the spreadsheet. Okay, 0.00207%. That's a very, very small amount. But that was 700 meters of water, and it can't expand in any direction horizontally or down. The only place it can go is up. So all that expansion is upward, and if you do the math, it works out that that 700 meter thick layer will expand upward about 1.5 centimeters for that tiny little change of temperature. Okay, 1.5 centimeters is not a huge change in the depth of the ocean. You're not going to go to the beach and notice that the ocean is 1.5 centimeters higher. You're going to notice things like it's high tide or it's low tide, where the water has maybe even moved as much as maybe a meter or something like that. Tides are very fickle as to how much they move, but they're going to be a lot more than 1.5 centimeters. On the other hand, this is something we can monitor. We can monitor the height of the ocean with lots of different technologies, and we have been monitoring the height of the ocean all the way back to the 1870s, and I would guess that if you are in a class like ATS EVS 105, you are aware that the world's overall, the oceans are increasing the sea level is increasing. Weirdly, this particular figure is just change in sea level since the beginning of the record in terms of inches. Inches? Whatever, inches. Very scientific sounding. And you can see that the total trend seems to be in pretty good agreement. They'd be right around, since the 1870s, so we're talking about 130, 140 years now. We've got about an 8-inch increase in sea surface temperature, sea surface height. 8 inches higher, that doesn't mean 8 inches farther up the beach. That means the ocean is 8 inches higher. That could be a long ways up the beach farther, depending on how sloped the beach, is and so on. But 8 inches is still not exactly we're drowning our cities just yet. Okay, this is a big sea level change, but in fairness, on geologic timescales, sea surface height changes quite a lot. I mean, there have been many times in Earth's history, for example, where Alaska and Siberia were connected because the sea levels had lowered enough that there was a land bridge between the two. The same with England and France across the English Channel. Many times in Earth's history, England has been physically attached to France because the sea levels were lower enough that you could just walk across what's now the English Channel. I mean, that's obviously way bigger than an 8-inch change, but see, there weren't people building huge chunks of infrastructure right there on the shoreline back then, right? We do something very different here. We build stuff right near the shore. That's why we monitor this stuff with pieces of equipment like tidal gauges. Okay, a tidal gauge works pretty much the way you suspect something like this would have to work. It's basically a toilet float. okay, for the tank on your toilet, okay, that's basically just there, and it's measuring how high the surface of the ocean, and these things are actually operated for use by mariners, okay, so that they know, like, how high the tides are and so on, and it reports back, and then there's ways that mariners' radio networks and things like that can tell them the tide heights and so on. They're also, by the way, we monitor the height of the ocean from space, which is totally astonishing. It's called radar altimetry. And these satellites in space actually shine a beam of radiation down to the surface of the ocean, and then the radiation reflects off the ocean and comes back to the satellite. How long it takes for that beam to go from the satellite to the surface of the ocean and back tells it how far the satellite is from the surface of the ocean. And believe it or not, they can actually measure that closely enough that they can actually tell, like, to the millimeter how high the surface of the ocean is at that location that the satellite is shining on right now. That's amazing to me. Actually, just recently, you might have seen a new satellite that's going to be doing this was launched. It's called Jason 3. It was launched by one of those cool private space companies, I think it was SpaceX, that tried to bring the rocket back for relaunch, for reuse and so on. Anyway, that was a cool little detail, but it's amazing to me that we can do this. And in fact, we've been doing this for decades. It doesn't seem like that would be an easy thing to do, but monitoring the height of the ocean from space has been going on since, like, at least the 80s. Okay? It's a fairly straightforward thing to measure. We measure, we know that grounded ice is going to be the problem as it melts and flows into the ocean. We know thermal expansion of the ocean is going to be important for the increases in sea level change. One thing that doesn't matter that people often think will be is icebergs. Icebergs, as they melt, they don't change the sea level. The water, they've already displaced some water by being an iceberg, and when they melt, they just fill in their own spot with the water that melts. So icebergs melting and other forms of sea ice don't actually change sea level at all. Now, how much are we talking about? How much change in sea level is possible? How much have we observed? We know it's only a few inches. What if we melted all the ice? What if we warmed the ocean quite a bit? Well, as you'll see in a little while, if we melted all the ice, we'd be talking about increasing the sea levels by like 100 meters. Wow, that's a lot. But we're not going to melt all the ice even in the next 500 years or something like that. That's not a very likely outcome. Even if we did, though, not very much of the surface of the Earth is closer to sea level than 100 meters. It isn't like we're going to bury the surface of the Earth in water if all the ice melts or if the ocean warms up or something like that. What I'm showing you here is the opening scroll, showing this Universal Studios was who made the movie Waterworld. You might remember this old Kevin Costner movie. And the premise of the movie was that all the world's ice had melted and the sea levels had risen until we live on a planet with no land. Okay, that's silly. Okay, even if we melted all the water in the surface in the oceans, we would not. We melted all the water. Even if we melted all the ice in the oceans, we would not bury all the mountains. We wouldn't bury all the cities or anything like that. That's a silly thing. Same with, you can find any number of silly pieces of Photoshop work that show, like cities underwater and stuff like that. Well, this is a substantial sea level height change to have made something like this happen. That's not in the cards anytime soon. But that doesn't mean that the rises in sea level are somehow trivial or something like that. Quite to the contrary, they're a very real and very serious problem. About 10% rather of the world's population lives within 30 feet of sea level. Again, 30 feet of sea level the oceans aren't going to rise 30 feet. But we're trying to get a sense here of how many people are actually in danger of having to be displaced and so on due to sea level rise. By the way, you can actually find all kinds of lousy figures about how many people live close to the oceans and stuff like that. That link that I provide there, that's an actual, it's an NPR story about an actual scholarly study that, did it right and figured out how many people were within 30 feet of sea level. Now, again, if you live 25 feet above sea level, it isn't like you're going to be swimming, okay? The sea level is not likely to rise 25 feet anytime in the next few centuries. But for every inch that the water does increase in height, there's an increased risk of damage during storm surges. A storm surge, when certain kinds of storms like hurricanes and big cyclones come ashore, they increase the sea level as the winds of the storm push ocean water towards the shore. Take ATS EVS 113 and I'll be glad to tell you all about that when we learn about hurricanes. But when a hurricane or other cyclonic type storm makes landfall, it increases sea level. Well, that's already a problem and causes flooding. But if we put that on top of there, another 8 inches of sea level increase that's just due to global warming, well, that's that much more water coming ashore. And that doesn't mean the water is going to be 8 inches farther up the beach or something like that. It means it's going to be 8 inches higher. That might be miles farther inland, over, say, southern Florida. Wow. All of a sudden, you're talking about a lot more people, a lot more affected. Now, admittedly, only during the extreme event of a hurricane landfall, but we got to be prepared for those too. It increases the risks due to prolonged flooding. It takes longer for rivers to drain if they're draining into higher sea level, if the sea levels at the bottom of the river are higher. I mean, especially down low in the estuaries where the rivers are draining into the ocean. Flooding events just take longer. There's prolonged flooding when you have higher sea levels. In terms of dollars spent, infrastructure problems are a huge deal. It's already a daily battle to keep the New York subway system dry. Okay, New York is right there at sea level. Things below the city are clearly below sea level. The pumps are right at sea level. The electrical systems are all at sea level. Every inch of sea level rise makes it more and more difficult to keep the subway system dry, to keep the sewer systems draining the right direction, to keep the electrical systems that are buried dry, etc. All these kind of infrastructure problems get worse with every inch of increases in sea level. That's before you get to the more dramatic and human interest type stuff, like people who live on low-lying Polynesian atolls or things like that, where the whole island might only be a few meters above sea level. Every inch of increase of sea level makes it harder and harder to find places that you can reliably live, even during a storm or whatever. Salt water is getting farther and farther up onto the island, etc. Okay, before we go on and talk more about ice particularly, I do want to ask a few questions about the observed changes that we have seen in the ocean. Question 1, moored buoys. Moored buoys can provide blank observations of blank below the surface of the ocean. That first blank is either going to be remote sensing or in situ. Oh yeah, I gotta remember those terms from the previous lecture. And then what are we observing using moored buoys? Temperature or the amount of ice? Alright, take a look. Follow one of the 4 links below this video to get some feedback about your answer before we move on to question 2.